Hi, this is Physics 1, Chapter 4, Part 2, and we left off, we were about to get into what's called free body diagrams. And this is probably one of the most important parts of Physics 1, and it's because it's really um, a very basic but important step in understanding what's going on with the problem and how to visualize it and what to look for. When I was in high school, the instructor mentioned about learning these and how it'll pay off in college and all that. What he neglected to mention was that we always teach this in college. He acted like that was something new. Um, but yeah, this is something very important that we use all the time. Um, and even if you were like a high-end scientist, you may still make a free body diagram to understand what's going on and to see what's going on. Well, there's other things that you may not do. If you ever watched the show The Flash, they have some scientists on there, or at least they're supposed to be scientists, and they're super smart to where they make particle accelerators. And they may put something on there like this, which you may see in a high school. And it's pretty simple, but the point of this would be to understand how to use this equation, and you wouldn't use this if you know algebra pretty well. So the fact that you see this on one of the scientists' board is actually kind of unrealistic. But if they were to see a free body diagram, which actually is kind of simple to do, um, it's actually something that would be common to see on somebody's board. Right? And so what we're doing is we're basically drawing a simple picture, but we're breaking this down. So here we have this picture. We have a weight that's 10 kilograms, a mass that's 5 kilograms hanging from a pulley, and we're going to break this down into the two objects. So we're going to look at the forces on this object and then the forces on this object. Okay, and I tend to label these, so I would write 10 kilograms just so I know that's that 10 kilograms and 5 kilograms. Okay, now this is one thing I do, not everybody does that. And then we look at the forces. Well, each one of these has a weight, and that's going to be one of the forces. So that's a weight and a weight. And that the idea that these should be kind of equal, so if that's that length, maybe this should be half the length, since it's half the mass. For me personally, I tend to not worry so much about the lengths of the arrows, um, because I'll use the numbers to know what they're supposed to be. But technically, they're supposed to be the same. They're supposed to be kind of to scale. A lot of times, though, we can't make them to scale, and that's why I just don't worry about it. And so we have both have weights. This one has the table pushing up. And I'm going to use the force we're going to call it now. We're going to call it normal force. Alright, and I'll be describing these forces at the end of these videos, or this video. This one doesn't have a normal force. There's no table pushing up on it. There's no, it's hanging in the air, so there's nothing pushing up on it. What we do have connected to it is a rope or string or cable. That's probably the best name for it, a cable. And so we have this cable pulling up, because this mass, since it's connected to it, is kind of helping this cable pull this up. And this cable, since it's being pulled, it's going to be in tension. So we have tension pushing up. And then that tension, that cable is connected to this 10 kilogram, and that's also going to be pulling. And this mass is using that cable to pull down on this rope. And so we have tension being applied that way. And you may, since this is on a table, that table may not be, a smooth, frictionless surface, so there may be some friction here, and maybe it's small. It may not be a whole lot, but there's going to be a friction force. Alright, well here there will be no friction. And so this is what the free body diagrams will look like. This is for this part of it, and this is for this part of it. And so we will use these to look at the net forces and figure out what's going on. And there's a couple of things we can say with this. The normal force is going to equal the weight of the 10 kilogram. I'll specify it down here, 10 kilogram, 5 kilogram. There's no guarantee that this weight and this tension are equal. Okay? We don't know what's going on. It could be that these are sliding. It could be that these are at rest. We don't know yet exactly what's going on. But we do know that this table is going to equal the weight, because I doubt there's going to be anything about it breaking the table. These two tensions are the same. That's why I didn't label them differently. They are the same. As long as it's the same cable, it's the same tension. Now, there is one other thing I want to mention, and this deals with pulleys. I'm going to make certain things a certain XY coordinate system. So X, Y. We're going to make down negative and left negative. That makes this tension positive and this normal force positive. When we go over a pulley, the cable, you follow the path of the cable. So if this is negative, then on this side, up is going to be negative, and down would be positive. Now the values of these are the same, but the fact that it's negative just means that it's going in a different direction. Right? So we go over this cable, and you get a negative tension and a weight that's actually positive. Alright, so let's look at some more. We have a physics book on a table. The table will push up, and that'll be your normal force. Physics book will pull down, and that'll be your weight. As far as we know, there's nothing else. Nobody's pushing to the left or right, so we don't even have to worry about friction. Just up and weight being down. A large crate is being pushed leftward at a constant velocity. Okay, so, before I go to this one, because it's just sitting at rest, we can say that the normal force equals the weight. Okay, or that we can say normal minus the weight equals 0. Alright, a large crate is being pushed leftward. So it's being pushed this way. Any kind of push, we usually just call it applied. And sometimes if you're applying it with a cable, we can call it either one, applied or tension. Naming the forces can sometimes just be a little bit redundant with some of them. And so you're applying the force to the left. Now we're assuming this crate is sitting on something. So there's going to be a normal force up, and there's going to be gravity down. And because we're applying constant velocity, for this to not have a net force in the x direction, we need something going this way. Because we need the applied force minus something else to equal 0. So what's going to be kind of going against this applied force? Well, that would be friction. So applied force minus friction equals 0. Normal minus, I say gravity, would call it weight, equals 0. Okay. Next one, a skydiver is falling and it has reached a terminal velocity. So skydiver is falling. His weight is what's bringing him down. Terminal velocity just means your velocity is equal to some constant. Okay, it's the highest point you can go. It's not increasing anymore, can't decrease. That means your forces have to be equal, which means this weight has to equal the air resistance, so air drag. And then you're at constant terminal velocity. Before you hit terminal velocity, what's actually happening is your air resistance isn't as high, because your weight's always going to be the same. So as you fall faster and faster, air resistance gets higher and higher until it finally matches the weight. It can't go any higher than this, because if it goes any higher than this, you start going up, and you can't go up. Or it can say you're starting to slow down as you fall, and that can't happen either. So you just reach a terminal velocity. Right, this next one, a sledded, that should probably say sledder, has reached the bottom of a hill and is coasting rightward while slowing down. Right, so we're at the bottom of a hill. I'm going to draw the, no, I'm not going to draw the hill. Just imagine the hill. You're at the bottom. So you're coasting rightward while slowing down, which means you're going to have some friction since you are slowing down. Otherwise, you're going to go straight and not slow down. You just keep going. So you have to have some friction with the snow. It may not be a lot, but there's going to be some. And you got nothing pulling you this way. That's why it's slowing down. You're moving this way. You move this way, but your friction is going opposite. You're going to have your weight, and you're going to have the force of this, ground up. So you have your normal force. A push that you may have did at the very top doesn't come into play here. That's long gone. That happened a long while ago, different scenario kind of thing. Okay, if you notice a lot of these, you have what's called equilibrium. Up here you had equilibrium. For this crate you had equilibrium. Okay, it's moving at a constant velocity or it's at rest. You actually have equilibrium in this one since it's a constant velocity. And the air resistance minus the weight equals 0. Okay, this one you did not have constant velocity, you had acceleration. And so not in equilibrium. Okay, because there's like acceleration, which means you have a net force. Which is going to equal, in this case, the force of the friction. Right, so wherever that friction is. So you're in equilibrium whenever you have a net force of 0, meaning an object's at rest, meaning there's something that is countering all the forces, or when an object is moving at constant velocity. So in other words, an object in equilibrium has 0 acceleration. So if you have acceleration, slowing down, speeding up, changing direction, then you're not in equilibrium. This becomes a main focus of statics, because we want everything to be in equilibrium. We want a roof or a cantilever coming off of a roof or a building. I should say that. So let's say this is the door down here. somebody walking in. You got this cantilever. And say they even put a little fence around it. It's kind of in the city. Whatnot. You got a cantilever. We don't want that falling. We want this in equilibrium, which means we want all the forces to cancel out. We don't want any acceleration. Otherwise, there's a problem. And that's part of what we'll get into. This is probably 3/4 of what we'll get into when we get into statics. Alright, so I mentioned a lot of these different forces. And so I'm going to go through and kind of look at each one of them. And it will really help because you want to identify these forces as best as you can in these terms. And I'll even write kind of what the symbol of these are. So that we'll use. And some of them have more than one. And it doesn't matter which one you use. I'll use a few of them. But you're going to have the forces. So we're going to start with the name. And then the idea behind it. Then the direction. And then the symbol. Okay. So first force. The normal force. Okay, we can think of this as the surface force. It's only applied if you're sitting on something. The direction is always perpendicular to the surface. So we see here, if it's a wall you're leaning against, so at her foot and at her back, you have a normal force. Her foot on the ground, you have the normal force coming up. It's always away from the surface. Okay. If you have, let me see if I can draw on this. Yeah. You have something on a hill, the normal force is at an angle. Right? So it's always perpendicular to the surface and away from the surface. And you'll either see N for the normal force, or you may see F of N. Sometimes I just write out normal, but usually one of those two is what's going to be seen. Next big one is gravitational force. And you think of this as the weight or force due to gravity. Okay. This is always pointed down towards the core of Earth. There will be a time where we're going to break gravity into two components. We'll get into that later. But it's pulled towards the source of the gravity, so towards Earth. And again, we refer to it as a lot of times as weight. And so you see it as weight. You'll see it as Fg a lot of times. You may even see it as mg. Mg is because how you calculate the weight. Weight is mass times gravity. Okay. This is a force. This is not little g. Okay, so it's not 9.8. G is equal to 9.8 meters per second squared. This is the force. So that's the acceleration. You have to multiply by mass to get gravitational force. So sometimes I'll just write mg instead. That way it allows me to label the m as well. Sometimes you may just see it as a weight. Sometimes you may see it as Fg. Pretty much it always exists on Earth. Always present on Earth due to gravity. So when you forget this force, it's a big one that you're forgetting. Then we got the spring force. This is present in any kind of elastic objects, particularly springs. Okay, and it's the force due to objects' elasticity, its ability to um, snap back to its original position, and it always opposes the applied force. Right, so if you have a spring, you put a force on the spring in its side is creating a force to pull that spring back to its original. So if you pull on a spring, the spring wants to pull back to its original shape. If you want to push in on the spring and compress the spring, it wants to push out to its original shape. So it can be inwards or outwards. And so it resists any compression or stretching. A lot of times you'll see this sometimes as Fs or maybe even F spring, especially if friction's involved, because sometimes you'll see friction with an S too. I'll explain that later. Or you may just see it as Kx or negative Kx, which that deals with its equation as F equals negative Kx. And the reason K you may see as a positive K is because this negative sign just means that it's opposes applied force. So if you made the applied force negative, this becomes positive. K is its elasticity, and we'll get into that later. Tension. This is present when cables, ropes, strings are pulled tight. And it's due usually to an applied force. And so sometimes we would just call it applied force. So you may refer to this as a FT or just a T or even just an applied force. Because maybe you're using an applied force to apply a force, or you may be using a cable to apply a force onto an object, and so this may be more important than the fact that it's tension. Right. So with Tom Cruise here, Ethan Hunt, that's it. He hanging from cables. These cables have tension pulling up. The applied force is his body weight pulling down. The tension is pulling up. And so it opposes the applied force. But when you have a cable, you will have forces on both sides that are tension, that opposes one another. And these are usually connected to objects that are part of the reason why there's a force being applied. Alright, so I don't want to erase all this right now. Let's go over. Next one is friction force. Oh wait, hold on a second. Let me go back. I'll grab the names. Start on this side. I didn't write straight, obviously. Alright, so friction force. Okay, this direction is one of the most important things. It opposes motion or possible motion. Right? So the idea is this is a force along the ground that's applying a force to an object moving along it. So what do I mean by motion or possible motion? Well, you can have two kinds of frictions. You can have what's called kinetic, and this is when the object's actually moving. Or you can have static. This is when object is not moving but could move if friction wasn't present. Okay, what I mean by that, you have a book on the table, there's no friction there, and this book's not moving, so there's no possible motion. The opposite thing is if you have a car on a hill, and you say it's parked, this car can move down the hill. But if it's parked and you have the brakes on and there's enough friction pulling up, and the reason it's pulling up is because this car wants to possibly move down, you have what's called static friction. Okay, now if this friction car was to start sliding, meaning let's say it rained, and so the road got slippery and the brake wasn't strong enough, it starts sliding, then it reverts to kinetic friction and you have moving. So we have two types of friction. So the symbols can get really confusing with this. You can have F of F, which is just basically the friction force. You could have Fs, which is the static friction. You can have Fk, which is the kinetic friction. And you can write them kind of as how you calculate them, as in U mu S times the normal, or mu K times the normal. Because for kinetic friction equals mu sub S times the normal. For static, mu sub K times the normal. And static is mu sub S times the normal. So you see, multiple ways you may symbolize these. Okay, air drag. This is kind of friction due to air molecules. We really only see this, at high speeds, really high speeds. So we don't really worry so much about it. Object falling off, a second-story window, we're not going to really worry about it unless the object is really, really small. So a lot of times we do neglect it. The direction is very similar to friction. It opposes the motion. However, I don't think there's any way it can oppose possible motion. So it's just really opposing the motion. And usually the symbol will either call it air drag, or maybe F air, something like that, F drag, something like that. We don't use it as often, so there's not really that specific symbol that we use a whole lot. Then the applied force. These are just any kind of push or pull. Okay, so push or pull. Push is if it's in the direction opposite from which it came, so you're pushing on that door. Pull is if it's in the direction from which it came, so you're pulling back. So you can have it kind of be like this, that would be a pull, or you can have it kind of like this, that would be a push. Either way, the arrow notes the direction. That's what really matters. And symbol, you may have it FA for applied, maybe just F for applied. Sometimes, because sometimes if you're applying it to a cable, you may use it as a tension. Really, this is kind of the big force that kind of traps any other possible forces. The last thing is the buoyancy force. By that, what I mean is, let me go back to applied force real quick. Any other possible forces, things like thrust. It's kind of applied force because of an engine. Lift. Applied force because of the wind pushing up that we had. So things like that can kind of fall into just applied force. Buoyancy. You are applying a force upwards from a fluid. Right? So a symbol is usually FB. We're going to talk about this more in chapter 10. This is force due to fluid molecules pushing up. And buoyancy is always going to be up. Well, I shouldn't say that. Buoyancy is going to really, I would say, yeah, buoyancy is pretty much going to be upwards. Yeah, applied upwards from fluid. Okay. Let me see where we're at. Okay, so I'm going to stop it here. We'll get into Newton's second law, and I'll probably do Newton's second law in one video, and then I'll try to finish up Newton's third law in another video, and we'll see if it takes even more than that to really finish this. Alright, so I'll see you in the third video.